Hello everyone, welcome to physics classes. I am Sarabdeep Kaur Sidhu here. So today we will discuss a very important and interesting topic, that is Miller indices. So let's start. Miller indices and crystal planes and directions. So in the previous lectures we have studied that in a crystal there are planes and direction. Now how to locate these planes and direction, because these planes and directions contain large concentration of atoms, and the concentration of atoms, or we can say atomic density, is different for different planes, because crystalline solids are anisotropic in nature. The physical properties are different in different directions. So how to locate these directions and planes? So first, how to locate the directions? So to locate the direction, this is the figure which describes two-dimensional and this is three-dimensional. So when we want to locate the directions in two-dimensional, so let's this arrow and this arrow, this shows the direction. Which starts from O, origin, and this is two-dimensional crystal lattice. Okay? Then A is the end point. Similarly, O is the starting point, origin, and B is the end point. So these are the arrows, are the directions. Now how to describe these directions? So these directions are described by the first whole numbered point. These are described by first whole numbered coordinates of, or we can say that coordinates of first whole numbered point, say x, y, and this direction must passes through this point. So this direction is described by first whole numbered point. So how first number whole point? Say this direction, which is described by this here A, arrow at A. Now the first whole number, so if we calibrate, this is 1, this is 2 centimeter, this is 3, similarly 1, 2, 3. Now the coordinates of first whole number point is this, first whole number point is this point. Clear? So the coordinates of this first whole number points are 1 on x-axis and 1 on y-axis. So this point is 1, 1, 1. So first direction, this direction is described by xy means 1, 1. Described by 1, 1. Clear? Similarly, second direction, that is this direction. Now in this direction, and this point passes through this one. So the first point which passes through this direction passes through that point, and that point must have whole numbered point. So first whole number point, suppose 1, this is not whole number point, this point. So second point 2, when we join this 2, and this is 1. So this is first whole number point in this direction. Clear? So on x-axis coordinate is 2, and on y-axis the coordinate is 1. So for second direction, the coordinate xy is 2 and 1. So I am again repeating that directions are described by the coordinates of first whole number point. That is xy, and this direction must passes through this point. Clear? And in three dimensions, so this is a unit cell in a three-dimensional crystal lattice. So take any direction. Suppose we are taking this direction. This is A. This is origin O. So direction O. This is a starting point is O and ending point is A. Clear? This arrow. So what are the coordinates? So in three-dimensional, the direction is described by again coordinates of first whole number point, that is x, y and z. Clear? X, y and z, and in three-dimensional we enclose them in a square brackets, direction in a square brackets. So OA OA is described by, yes, only it is on x-axis it is 0, y-axis take this distance 1, and z-axis also 0. You can also skip the commas. So, and in square brackets, So, this is 0, 1, 0. 0, 1, 0. So, OA. This is 0, 1, 0. And similarly, take another point. If we take this B and this arrow, okay, this is another direction. So, what are the coordinates of first whole number point OB, that is equal to, yes, if we take where the unit cell cuts the x-axis, y-axis, that point is 1. So, if this is 1 and on y, it moves on x-axis 1, y-axis 1 and z-axis 0. So, the 1, 1 and 0. 1, 1 and 0. Clear? You can skip commas from this 1, 1, 2, 1. You can also put commas or skip commas. Clear? So, directions in 2-dimensional as well as in 3 dimensions are described by coordinates of first whole number point, and that direction passes through that point. Clear? So, this is about the direction. Then is about the crystal planes. Okay, direction we have studied. Then about the crystal planes. Clear? So, crystal planes. So, in a crystal lattice we can say that a set of lattice points, array of lattice points. Clear? But in also it is regarded as a made up of an aggregate of, I will explain, aggregate of set of parallel equidistant planes. Aggregate of set of parallel equidistant planes passing through the lattice points. Clear? And which are known as crystal planes. So, how? So, take an crystal lattice. So, if this is a crystal lattice, these are the lattice points. When space lattice join with the basis form a crystal lattice. Okay? So, these are the lattice points. Now, when we join these points like in this way, we can join, clear, one set, and also we can join these points in this way, in this way, in this way. Clear? And also we can join these points in this way, in this way, in this way. Also in another way. Clear? So this set of, when we join these points in this way, so this is one set of parallel planes and equidistance. Clear? And this is another set of parallel planes, and this is another set of parallel planes. So that's why we can say that crystal lattice is made up of a aggregate of set of, aggregate means this type, and this type. Okay? Aggregate of set of parallel planes, parallel equidistant planes. Clear? And passing through lattice points, because these planes are passing through these lattice points. So these planes are called crystal planes, and crystal lattice is also made up of these aggregate of a set of equidistant parallel planes. Clear? Now the point is how to designate these planes. So for this, Miller, who is a British crystallographer, Miller, he devised a Miller indices, three numbered system, which designate these set of parallel points. So Miller divides a system like HKL. So he gave a system which contained three numbers, that is HKL. Clear? That represent a parallel set of parallel planes. Clear? So now how to find out the Miller indices. Next point is how to. What is the use of Miller indices? Because I told that the atomic density is different for different planes. So to represent that different set of planes, Miller devised a system. Clear? Three numbered. This is one index, this is second, this is third. So combination is Miller indices. Now how to find out Miller indices? So for this we take any crystal lattice and take any plane. Take any plane. Suppose we take this is x-axis, this is y-axis, this is z-axis. Clear? This is origin O. Suppose this is we know that the fundamental translational vectors A, B, C. So this is A, this is 2A, this is 3A. Similarly, in this direction, this is B, this is 2B, this is 3B. And in this direction, this is C, this is 2C, this is 3C. Clear? Now take any plane which cuts these axes x, y, crystallographic axis x, y and z. Suppose this cut on x-axis at point 3. So 3, 2, 2. 3, 2, 2. 3, 2, 2. So here is 3, here is 2, here is 2. This point, and this point. Take this is A, B and C. So A, B, C, this is a plane which cut x-axis at this point A, on y-axis B and on z-axis C. So first point is first take the intercepts made by the plane on crystallographic axis. So first take the intercepts. First is take the intercepts made by the plane on crystallographic axis. Yes, or we can say that the coordinates of the intercepts. Now here is 3A. On x-axis it is 3A. On y-axis it is 2B. It is 2B. On z-axis it is 2C. Clear? So this is first step. Then second step is, what is the second step? Now take the multiples of A, B and C. Multiples of the intercept A, B, C. So if we remove A, B, C and we take only these numbers 3, 2, 2. So in the second step we take the multiples of the A, B, C. That is 3, 2 and 2. Clearly multiples of A, B, C. Then what is the third step? Third step is take the reciprocal of the intercepts. This is very important. First we take the intercepts made by the plane on the crystallographic axis, or we can say the coordinates of the intercepts. Then second point is take the multiples of A, B, C, 3, 2, 2. Okay? And third step is take the reciprocal of these intercepts. So what are the reciprocals of these intercepts? That is 1 by 3, 1 by 2 and this is 1 by 2. Clear? This is the third step. Now what is the fourth step? Fourth step is reduce these reciprocals into smallest set of integral numbers. So reduce these reciprocals to smallest set of integral numbers. So smallest set of integral numbers. So reduce them into a smallest set of numbers and enclosed reciprocal, that means reciprocal, enclose them into brackets parentheses. ठीक है जी? So the reciprocals of reduce them into smallest set of numbers. So reciprocals are देखो सीखे 1 by 3, 1 by 2, 1 by 2. Clear? Now smaller, take the LCM of 3, 2, 2. That is 6. LCM is 6. So multiply these by 6. So 6 into 1 by 3, 2. Reduce them into smallest numbers. 6 into 1 by 2, 6 into 1 by 2. So what you get? 2, 3, 3. 2, 3, 3. So now enclose them into brackets. So enclose them into brackets. So these are the Miller indices 2, 3, 3. Clear? So I am repeating again. We draw this diagram like this. We have drawn. So this is the origin, and this is here is 2 y-axis, 2b, this is 3a, and this is 2c. This is y, this is z, and this is x-axis. Clear? So I am repeating again. First take the intercepts, that is 3, 3a, 2b, 3a, 2b, 2c. Then take the multiples of a, b and c, that is 3, 2, 2. Then take the reciprocals 1 by 3, 1 by 2, 1 by 2. Then reduce them into smallest set of integral numbers. For this we take LCM of 3, 2, 2, that is 6. And multiply these by 6, we get this, and put them in this type of brackets, and we get the Miller indices. Now how we can define the Miller indices? Miller indices may be defined as the Miller indices may be defined as the reciprocal of intercepts made by the plane where on crystallographic axis, clear? See, when reduced to smallest numbers, integral we कह सकते हैं, integral number, smallest numbers. So these are Miller indices. Clear? See, then on the next topic, so you can write this. So Miller indices may be defined as the reciprocal of intercepts made by the plane on crystallographic axis when reduced to smallest numbers. ठीक है जी. Next we study features of Miller indices. What are the important features? So next is important features of Miller indices. Yes, important features. So what are these important features? So first feature is that when Miller indices are of single digit, then there is no comma between them. So if they are of single digit, then no commas between them, like 2, 3, 3 or 2, 2, 3. Okay, 1, 1, 1, 1, 1, 1, 2, 2, 2. So they are of single digits. So there is no comma between them. Clearly, first feature. Second feature, if they are of double digit, then they are separated by commas. For example, take an example 11, 6, 6, 10, 12, an example. So this is, they are separated by commas. They are separated. I am taking only the example. If they are of double digit, they are separated by commas. Clear? See? So, third important feature, what is that? All the parallel equidistant planes have the same Miller indices, or we can say these define a set of parallel planes. How? For example, if you have these are the coordinate axes x, y and z in a crystal lattice. So if a plane cuts the axis at these points, so at same intercept, here is also 1, here is also 1, here is 1a, here is 1b, here is 1c. So intercepts are 1, 1, 1. So their reciprocals are also 1, 1, 1. So Miller indices are 1, 1, 1. So for this plane, Miller indices are 1, 1, 1. So they are 1, 1, 1. And if there is another plane, we take parallel to this plane, and that is the cut the x, y, z axis at these points. So if this is also 2, this is also 2, and this is also 2. So it cut the x-axis, y-axis at 2, 2, 2, 2. Their reciprocals are half, 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 half. And if we multiply it by 2, then they are multiply it by 2, then 1, 1, 1, 1, 1, 1, 1. So these are also 1, 1, 1. Then again, if cut at another points, here is 3, here is also 3, here is also 3. So their intercepts are 3, 3, 3, 3, 3, 3. So their reciprocals are 1 by 3, 1 by 3, 1 by 3. And when we multiply by 3, LCM of 3, 3, 3, that is 1, 1, 1, 1. So 1, 1, 1. So they represent a same set of parallel planes. Or also we can say 1, 1, 1. If it here is 2, 2, 2, here is 3, 3, 3. They represents a same set of parallel planes. Clear? See? Then this is very important. And next point that is very, very, very important. If a plane is parallel, to coordinate axis, then intercept of the plane is infinity and hence index is 0. If अगर कोई भी plane जो है वो parallel है coordinate axis के, then it doesn't cut the axis at any point. So intercept is infinity, hence reciprocal of infinity is index, that is 0. So I will give you an example of this. For example, this is any unit cell in a crystal lattice. This is a unit cell of this type. You can take any type. So this is a unit cell, and these are the axes, x-axis, y-axis and z-axis, x-axis, y-axis and z-axis. Now take any plane. So if I am taking this plane A, B, C, D, clear, this plane. Then what about this plane? We want to find out the intercepts of this plane, clear? So the intercept of this plane on x-axis. So on x-axis, this plane is parallel to x-axis. So it doesn't cut the x-axis at any point. So their intercepts are infinity, clear? And along y-axis, it cut the y-axis at this point. So we take it 1, intercept 1. And along z-axis, this is also parallel to z-axis, so doesn't cut the z-axis at any point. So intercept is infinity along z-axis. So reciprocal of this is Miller indices, and we put them in a brackets. So 1 over infinity is 0, 1, 0. So Miller indices of this are 0, 1, 0. Similarly, you can take any example. If you are taking this A, D, E, F, this plane. A, D, E, F, this plane. So this plane is parallel to y-axis, clear? and this plane cut the x-axis, and along z-axis it is also parallel. Clear? So a plane which is parallel to any axis, it doesn't cut that axis at any point. So Miller indices, intercept is infinity, index of towards that coordinate is 0. Clear? This is very, very, very important point. Then fifth point, if a plane cuts an axis on negative side, तो कोई भी प्लेन नेगेटिव साइड पे कट कर रहा है, then what of the origin, negative side of origin, then corresponding index is negative because intercept is negative, so index is also negative. So how we can represent that index, negative index, by putting a bar on it? How? For example, I take this as a, for an example, I take this as an unit cell and taking this as this as x-axis, this as y-axis, and this as z-axis. And if we take this plane A, B, C, D, A, B, C, D. Now what about the intercepts of this plane made by this plane on coordinate axis? So along x-axis, this is parallel to x-axis, so intercept is infinity. Along y-axis, it cut the y-axis. If this is origin, then what about its axis? Yes, if this is origin, what about its axis? Because this is origin, then its axis, it intercepts along this y-axis is negative on negative side, so we can take that 1, negative minus 1. Clear? And along z-axis, it is also parallel to z-axis, so along z-axis infinity. So Miller indices, infinity, 0, minus 1, 1, minus 1, so we put 1, that is bar on it, represented by bar on it, and this is 0. So 0, 1 bar, 0, or we can say putting HKL, if HK bar. Clear? So these are the important 5 features of Miller indices. Clear? And there is another important point, that is direction, HKL direction. This is an assignment for you all. HKL direction is represented by square bracket. Direction HKL is perpendicular to HKL plane. HKL plane means plane having Miller indices HKL in cubic crystal. This is also a feature of Miller indices, cubic crystals. So prove it. This is an assignment for you. So thank you very much.